Okay, thank you very much for the introduction. And today I'm very glad to be able to be here to talk to you about our recent work on Tamari intervals and blossoming trees. And this is a joint work with FPSAC and Philippe Nadeau, who has just gave the talk half an hour ago. And we'll be talking about blossoming trees, as you can see. So we'll start with the basic objects, which are binary trees. A binary tree of size n is simply a plain rooted tree with n internal nodes, all of them of degree 2. So it means that there will be n plus 1 leaves. And then in this talk, we'll draw them in à la Chapeau, meaning that all the leaves will be drawn in a way that, such that it's all on the same horizontal line, like this. And it's well known that they are counted by cardinal numbers. Now we'll try to define partial order on all the binary trees of the same size using what we call the left to right rotation. It's very simple. We just look at a tree and we look at the patterns like this, any pattern like this, with 3 subtrees consecutive, and with the middle one branched to the left-hand side. And we only need to branch it to the right-hand side to obtain a new tree, and we say that a new tree is larger, slightly larger than an old tree. Now, if we take all such possibilities of moving from a smaller tree to a larger tree, and we take the transitive closure, what we get is the Tamari lattice discovered by Tamari in 1962. So here is an example of the Tamari lattice of order 3. And we can see that there are already some very nice symmetry on it, meaning that if we turn it upside down, it is isomorphic to itself. And the anti-isomorphism is, of course, given by just flipping the binary trees left to right. So this is also a self-dual lattice. And other than its nice symmetries, it also has deep links with other objects in combinatorics, as we have already seen in previous talks. For example, associahedra and weak order. And due to all these connections, it also has many generalizations. Now, given this lattice, the natural next step to study it is to look at its intervals. In this context, it will mean 2 binary trees. The smaller one, always colored red in our talk, that can be converted to a larger one, always colored blue, using the left to right rotations. So in this particular example, we only need to, well, branch this one and then branch this one to get the blue one. Okay? Other than the fact that this is a natural second step to go for the study of this, this structure, why are we interested in it? Well, it is because it's also related to other combinatorial objects. For instance, Bergeron and Préville-Adel conjectured that they are related to trivariate diagonal co-invariant space. And Chapeau studied them by means of operads and studied them for the means of operads. But for me, who is more like an enumerative person, I'm more interested because they have very nice counting formulas. And not only that, there are also many subfamilies of Tamari intervals that also share this property of having nice formulas. For instance, we have so-called synchronized intervals, which are in bijection with intervals in the new Tamari lattice, a generalization of Tamari lattice. We have so-called new modern intervals, which first appear in the enumeration of Tamari intervals by Chapeau. And they can be understood as irreducible elements in the operate of grafting on Tamari intervals. And the further restriction on modern intervals is called infinitely modern intervals. And the last one I'm going to talk about here are Crevarest intervals, which are intervals in the Crevarest lattice, so the lattice for non-crossing partitions. And of course, this Crevarest lattice embeds nicely into the Tamari lattice. So they are also Tamari intervals. And not only they have very nice numbers, but there is also some surprising fact that they are also in bijection with various families of planar maps, which are some kind of more geometric topological object. So what is a planar map? It's simply a drawing of a graph on the plane such that all the edges crosses only on vertices. And we define it up to continuous deformation. Okay, so here are 2 examples of planar maps, and you see that, well, on the pictures, there are some corners on the outer face, so the infinite face, that are marked. This is because we consider only rooted maps. We mark one of the corners to break the symmetries. That makes counting much more easier. And because they are drawings of graphs, so notions in graph theory naturally applies. So we can consider, for example, triangulations, meaning that all the faces are of degree 3, or bipartite maps, which means that the graph themselves are properly two-colored on the vertices. Okay, and all the families I talked about, they are in bijection with some kind of family of planar maps that can be resumed in this very large table, and we also have their formulas, which are also very simple. Okay, and not only that, Tamari intervals are also in bijection with other objects, other combinatorial objects. Some of them are defined in a more algebraic way, for example, interval posets or closed flow in forests. But there are also some others, more exotic ones, for example, fighting fish, which is a generalization of parallelograms, and lambda terms, which comes from computational logic. And there has been a lot of work on the enumeration and bijective study of these different families of Tamari intervals and their generalization, and there has been a lot of people working on it. And we have very rich results, much larger than this table, which was already large. However, there's something that's not that satisfying in this picture, is that for each line of the table, we see that, well, they are more or less the same kind of object. They are all Tamari intervals. They only differ a bit in the restrictions. However, at each time, when we want to get the enumeration formula or when we want to build bijections, they're different enough so that at each time we need to reinvent new generating function, new generating function, of course, but new functional equations, which looks quite close to each other. And the bijections, we also use ideas that are more or less the same, but we need to do a new one because they're sufficiently different. That's not so satisfying, and that's where our contribution is. That is, we are going to provide a unified framework in which we can do this big table all at once. Okay? And the central object of our contribution is something called bicolor blossoming tree, which is simply an unrooted plane tree, this time, unrooted, such that each edge is colored half blue and half red. We didn't pick this color on purpose, huh? The Americans know. And then when we look at each node, other than the adjacent edges, they also have butts, 2 butts. And the 2 butts will separate the adjacent red and blue half edges. So here is an example that you can check that all the conditions are satisfied, and locally, they will look like this. We didn't invent it. It was invented by Bruno and Schiffer in 2006 in the context of bijection and encoding of triangulations. And afterwards, there were many variants that were proposed, and they were used a lot in the enumeration of maps. And now our contribution is that we found that Tamari intervals of size n, they are also in bijection with this bicolor blossoming tree with n edges, so n+1 nodes. Our bijection was inspired by the work of Chardin and Bons on Tamari interval posets. And as I said, they give a uniform enumeration framework of what we are going to do. And our bijection is really simple. That means there are many enumerative and structural consequences that can be deduced from it.
Can you explain what you mean by splitting reds and blues? I don't know. These 2 bytes splitting reds and blues.
Okay, the question was explain a bit splitting the 2 colors. Okay, so it means that it's locally, when we look at a node, it locally looks like this. For the 2 butts, if we draw a line from 2 butts, well, the blue half edges are on one side and the red half edges are on the other side. Okay? So, before looking at the consequences, let's look at the bijection, which is not very difficult. Okay, first we will introduce another representation of Tamari intervals. Instead of drawing the 2 trees side by side, we'll draw the big one, the blue one, on top, and the smaller one, we'll flip it by the x-axis and draw it on the bottom. And of course, we can do it for any pair of binary trees, but we can show that such pair is a Tamari interval if and only if it avoids this pattern, meaning that there is a blue subtree strictly preceding a red subtree on the leaves, and they share at least one leaf node. Okay? And now we'll convert it to another drawing called smooth drawing. It's quite simple. We just look at any internal node. It will span to the leftmost leaf and rightmost leaf. And we will place this wedge, like this, by a semicircle linking these 2 points. Okay, and we do that for blue and red, and what we have is a smooth drawing. And the forbidden pattern for Tamari lattices, Tamari intervals, they goes well also with this bijection. Okay. Now we have an observation. If we only look at half of the smooth drawing, for example, the top half, we'll see that for each leaf, it's either always on the left-hand side or on the right-hand side of semicircles. This is determined by its type, meaning that it is either the left child or the right child of its parent. So if it's the left child of its parent, then, well, by construction, it can only be on the left end of semicircles of the arcs. If it's on the right, then it will be on the right. Okay? So this is an observation that we're going to use. Now, with the smooth drawing, which I think should be clear, we can obtain the blossoming tree by drawing a graph a bit locally. So how do we draw it? Well, we look at the segments on the middle line, so on the horizontal line, there will be n of them. And for each segment, we'll draw an edge that will be half blue and half red. For the blue part on the top, well, we look at the left node of the segment, and either it's on the right-hand side of arcs. In this case, we pick the highest one, and we'll look at where it lands, and we'll draw the half edge linking the landing point to the middle of the segment. Okay? For the red part, it is exactly the same, except that we're looking on the right. Or you can also say that we don't care about left and right. Anyway, we're just going in the counterclockwise direction. Okay? So in this way, we'll draw something. We don't know what it is, but we'll draw something that looks like this. And if we look at the forbidden pattern for smooth drawings, this will translate nicely into this, meaning that the forbidden pattern will be a blue half edge preceding a red half edge here, and they overlaps on at least one node in the middle. Okay? And now we see that, in fact, this is a blossoming tree. We just need to break the middle line so that they are buds, and we can now check the conditions. Each edge is half blue on top and half red on the bottom. Okay? The pair of buds on each vertex separates the top part that's blue and the bottom part that's red. So it's almost a blossoming tree if we can prove that it is a tree. Well, we are on good start because there are n edges and n+1 nodes. We only need to show that it is connected. And we already see that if we have a forbidden pattern here, like this, in fact, it cannot be connected because if we take the smallest such pattern, then there can be no edge linking this middle point in the overlap to anywhere outside. Because any such edge will create a yet smaller forbidden pattern, which is impossible. So the presence of forbidden pattern already says that it will not be, this will not be a blossoming tree. And we can prove by induction that the converse also works. So this is an if and only if. And we see that we have a blossoming tree here, if and only if what we had at the beginning was a Tamari interval. So this is the bijection. Very simple. You may complain a bit that it does not look like a tree. It looks like a licorice. Okay, just shake it a bit, and we have a tree. Now, we want to go back to the other direction. What do we do? Well, we have a tree. And what we only need to do is to find the order of the nodes on the horizontal line. And how do we do that? Well, we look locally, a bit locally, on the licorice drawing. we see that, well, we need to match the butt with the middle of edges. And we need to do it again in a counterclockwise way. Okay? So some of the butts, they can already be matched. For example, this one, it can go directly to the half edge, to the middle of the edge next to it. Some of them we cannot do immediately. For example, if we look at this one, well, when we go in the counterclockwise direction, it's blocked by another butt. It's not a problem. We do what we can. We match some of them, and then the others that were initially not enabled now becomes available. For example, this one, now we can match it here. So we do it again and again. And at the end, there will be two butts that are left because there are one vertex more than edges. Okay? Two butts left, and we can show that the matching lines, there will always be one line. There will always be one component. There will not be some loops. And if we look at the lines, we see that, well, for each line, that separates the blues and the reds. Because it does it at the middle of each edge, and it does it also at each vertex. So, to get back to the Tamari intervals, what we only need to do, it is to stretch the two butts so that the matching line becomes one straight line. And then what we will get back will be the licorice drawing of our blossoming tree, from which we can get back to the smooth drawing of Tamari intervals, and then the Tamari intervals themselves. Okay, I assume that you are convinced that this is quite simple. Now, because it's simple, it also transports a lot of statistics, interesting statistics. As we have mentioned, for each leaf in the binary tree, we can assign it to a type to it by saying that it is of type 0 if it's the right child of its parent, and 1 if it's the left child. And then for each node in the Tamari lattice, which consists of two trees, well, the types will be just two numbers, either 0, 0, 1, 0, or 1, 1. Why not 0, 1? Well, because if we have a 0, 1, so the blue will look like this, and the red will look like this, then if we look at its parents, their subtrees form a forbidden pattern for the Tamari interval. Okay, so we have three types. And it was first considered by Chapouton in the refined enumeration of new intervals, and he discovered that there were some kind of symmetries in it. Okay, but these statistics translates very nicely on blossoming trees, because we have already talked about that. The fact that a node receives an arc from the left-hand side or the right-hand side, it depends only on its type. And in the construction of blossoming tree, we see that only the left-hand side of blue arcs will receive blue half edges, and only the right-hand side of red arcs receive red half edges. So in fact, if we look at each type, what they say is the presence or absence of blue or red half edges in the blossoming tree. So 0, 0 would mean there's only red ones. 1, 1, it will mean there are only blue ones. And 1, 0 means that they are both. Okay, I clicked too quickly, but it's okay. Using this, we discover a recent result from Alan Boston, Frédéric Gisac, and Vincent Pilot on the number of Tamari intervals of size n with k nodes, either of type 0, 0, or 1, 1, and it was given by this very nice formula. Okay, but why are they interested in it? It is because it gives the F vector of the canonical complex of Tamari lattices. And this also generalized what we call the synchronized intervals, which are intervals with only nodes of type either 0, 0, or 1, 1. So they're always the same, so synchronized. Also, and this is the special case, k equals to n plus 1. So this is really nice, but the problem is the way they obtain them is not so nice, because it involves solving a functional equation and doing more algebraic stuff, algebraic manipulations. But with our blossoming tree bijection, we can do it quite easily. We first observe that the factor in the middle has a very nice interpretation, meaning that we are picking k nodes among n plus 1. so that they will be of type 0011. And if we look back to the previous slide, 0011 simply means that there are at least one group of color that's absent, meaning that the two buds are adjacent together. And we can kind of fusion them together. And afterwards, we can use a cyclic lemma kind of argument to get the rest of the parts of the formula and for connecting the blossoming tree. So what we have is a purely combinatorial proof of this result, and it's really nice. And not only that, our bijection, because it's so simple, it also goes well with the duality of self-duality of Tamari interval, of Tamari lattices. So we recall that the duality acting on Tamari intervals would be just exchanging the larger and the smaller tree and flipping both of them left to right. But if we look at the canonical drawings, it simply means that we'll turn the canonical drawing 180 degrees, so upside down, and we exchange the colors because we have the colors in some way. Okay? But if we look at our bijection on blossoming trees, we see that we don't care about left and right, things like this. We are just turning counterclockwise. So the image, the blossoming trees corresponding to the interval and its dual will be exactly the same, except that the colors are changed. Okay? And more than that, all the interesting families we talked about, they can be described by forbidden patterns in the blossoming tree. So for synchronized interval, it's just a node with edges on both sides of its buds. And for modern intervals, it's the presence of an edge such that on each of the extremity, if we turn in a clockwise order, clockwise order, we'll always encounter an edge instead of a bud. Okay? So this is a forbidden pattern. And for infinitely modern, which is a further restriction, instead of only looking at an edge, it will be any path. And we do the same checking. For curvaceous intervals, it's also the same, except that it's the mirror. So instead of looking clockwise, we're going to look counterclockwise to check the conditions. So all this description with forbidden patterns allows us to give alternative bijective proof of some of the families, some of the correspondence we have seen in the spirits of Boulon-Schaeffer, which uses a kind of closure, as we have seen in the previous bijections, to obtain from blossoming trees the corresponding planar maps. So for the general interval, it's exactly the same, exactly the bijection of Boulon-Schaeffer to convert them into triangulations. For synchronized intervals, the restricted blossoming tree, they can be converted to some variants that are in bijection with non-separable maps. And for curvaceous intervals, it's even easier because we look at the restricted blossoming tree and it breaks naturally into three parts recursively. So it's in bijection with ternary trees. Okay, and this is bijective proof. And on the enumeration front, we can do the enumeration of all these families using tree specifications, so the decomposition at the roots, because all these forbidden patterns can be accounted a bit locally. So this gives a uniform way to do the enumeration because we know how to enumerate trees under a given tree specification. And not only that, because we are doing the decomposition, so we can control the type of each node. So we can refine each enumeration by the number of nodes of each type. And we can also do intersection of families because it simply means that we are looking at several patterns at once. Last but not least, we can also do the self-dual intervals because it goes well with our bijection. It's just exchanging color, so we can enumerate those that are self-dual in each of the family. So here is the results. Here are the results that we obtained in a big table. 4 of the families we listed here are already studied before, and the new one is the intersection between modern intervals and synchronized intervals. And the general enumeration of general intervals, it was given by catalog numbers. And all the rest, we rediscover the formulas using our method. But not only that, we can also do the self-dual subfamilies of even size and of odd size, and all of this with exactly the same method. Okay, But of course, we are not stopping only at the enumeration. We also want to study the structures. For instance, we observed that the forbidden pattern for infinitely modern and Cavaras, they're just mirror to each other. So the reflection on blossoming trees, the exchange is a bijection between these two families. And it would be interesting to study what it does on general Tamari intervals. So a first question we can ask ourselves would be the image of the modern intervals, which would be which is a superfamily of infinitely modern intervals. So its image would be a superfamily of Cavaras intervals, and it would be interesting to understand what it is. Next is that Vic Reiner observed our paper, and he observed that the formula for self-dual intervals, they can be obtained by taking a Q analog of the formula for general intervals and taking Q-1. Okay, and we also checked that it also works on synchronized intervals, and we want to know combinatorially what it means. Our bijection is not almighty because we try it on M-Tamari intervals. It does not work because essentially M-Tamari intervals, it needs a certain order on the horizontal lines for the types, but our bijection break it, so it's not so nice. And then because our bijection is nice, we also implemented it in stage math along with a random generator, and we draw some very large blossoming trees, and it looks quite nice. It seems to have some large-scale structure, meaning that they share some circles, and there are some spiral structures, and it would be nice to understand it. Maybe a way is to use the recent result of Guillaume Chapuis, which will be presented tomorrow in the poster section on the limit shape of Tamari intervals represented in the thick path perspective. So that's all. Thank you very much for listening.
Okay, maybe one quick question for Wenjie over there. Wait, one quick question over here. You want to just shout?
Yeah, I'll shout it. So you said that you reduced the question to enumerating these blossoming trees. You can then put more restrictions and enumerate them. But what are the enumeration techniques that you use to enumerate them?
It is what I call the tree specification, meaning that we try to, the question was how we do the enumerations. And the technique is quite standard. It's a tree specification, meaning that we'll define several families of blossoming trees. And we'll say that, how do we decompose them? Well, when we decompose at the roots, then there will be a sequence of trees in a certain type plus a sequence of trees in another type, etc., which reflects the forbidden patterns. So we put these families to avoid these patterns, to account for the information to avoid these patterns. And then we have a system of algebraic equations, and we can either solve it stupidly or use some combinatorial insight to see that, the formula would be like this, and we don't need to solve the equation. Yeah.
Okay. Let's take the rest of the questions in the break and thank Wenjie again.